What if a 600-kilogram NASA satellite, about the size of a small car, was hurtling back to Earth? And the predicted impact zone was right over your home? It sounds like science fiction, but dozens of large objects, old satellites and rocket boosters, make uncontrolled reentries every year. For a long time, this was a distant, abstract problem. But that's changing. The skies above us are more crowded than ever, and what goes up must, eventually, come down. In this video, we're going to follow the final, fiery journey of a deorbiting satellite. We'll break down the physics of its descent, investigate the real odds of it finding you, and explore the much bigger, growing threat of space junk raining down from our increasingly crowded orbit. The final Plunge picture: a 600-kilogram satellite. For years, it faithfully served its mission, maybe observing solar flares, like NASA's RESI satellite, or monitoring our changing climate, like the ESA's ERS-2. But its fuel is gone, its systems are dark, and its orbit is slowly decaying. It's a gradual process, driven by the faint but persistent drag from the very top of Earth's atmosphere. Then, it crosses a critical line, an altitude of about 80 to 120 kilometers. This is where the real plunge begins. Streaking at orbital speeds of nearly 28,000 kilometers per hour, that's over 7 kilometers a second, it screams into the thicker atmosphere. The air ahead can't get out of the way fast enough. It compresses and creates unimaginable heat, with temperatures that can soar past 1,600 degrees Celsius, or 3,000 degrees Fahrenheit. This satellite wasn't built for this. It was made for the vacuum of space, not a brutal atmospheric assault. The first things to go are the fragile solar panels and thin aluminum skin, which melt and vaporize almost instantly. The main body of the spacecraft starts to tear apart under the extreme forces, fracturing into smaller pieces. Most of its mass, the wiring, the aluminum structure, the sensitive electronics, will simply ablate, burning away into what looks like a spectacular, fleeting meteor shower for anyone lucky enough to see it. But not everything burns up. Deep inside, some components are tough enough to survive. Fuel tanks, often made of dense titanium or stainless steel, have incredibly high melting points. Heavy flywheels used for stabilization and other robust parts can also make it. NASA and ESA assessments suggest that for many satellites, around 10 to 20% of the original mass can survive re-entry. For our 600-kilogram satellite, that could mean 60 to 120 kilograms of debris, fragments ranging from the size of a fist to an engine block, might actually reach the ground. What are the odds? So now you've got chunks of a high-tech satellite, some weighing a serious amount, hurtling toward the ground. The big question is, what are the odds they'll land on you? Statistically, they are incredibly small. And this is where we need to be really clear. When NASA's 300-kilogram RESI satellite came down in 2023, the agency calculated the overall risk of a casualty somewhere on Earth to be about 1 in 2,467. That number sounds a bit scary, but it's the total risk spread across the entire global population. Your personal odds of being the one hit are astronomically lower, closer to 1 in several trillion. There are a few key reasons for this. First, the Earth is huge and mostly empty. About 70% of our planet is water. A huge portion of the land is unpopulated desert, forest, or ice. The chances of a random fragment landing in a populated area are slim from the start. Second, predicting the exact impact spot of an uncontrolled re-entry is notoriously hard. Even hours before it happens, the uncertainty window can stretch for thousands of kilometers. The object tumbles unpredictably, and its path is swayed by ever-changing atmospheric density. When the ESA's ERS-2 satellite re-entered in February 2024, its final impact zone was confirmed to be over the North Pacific Ocean, far from anyone. It's a game of probability, and the house, meaning the ocean or a desolate landmass, almost always wins. However, the conversation is starting to change. The individual risk is tiny, but the aggregate risk, the overall, collective danger, is growing. We are launching more objects into space than ever before. Some experts now warn that with the growth of massive satellite constellations, we could reach a point where falling debris injures or kills one person on the planet every couple of years. The sky isn't falling, but we are filling it with things that will, eventually, fall. A history of falling junk. This isn't a new problem. Things have been falling out of orbit since the space age began. In 1979, the enormous 77-ton Skylab space station made a spectacular, uncontrolled re-entry, scattering debris across the Australian outback. More recently, in 2020, Fragments from a Chinese Long March 5B rocket stage damaged several buildings when they landed in Côte d'Ivoire. These Long March 5B incidents have become a major point of international criticism. Unlike most modern rockets, which are designed so their large stages make a controlled fall back into the ocean, the Long March 5B core stage reaches orbit and is just left there to tumble down uncontrollably. These are huge, 20-ton objects. After a series of these re-entries since 2020, NASA's own administrator has repeatedly slammed China for failing to share tracking data and for taking unnecessary risks. So far these events haven't caused any injuries, but they highlight a dangerously reckless approach to orbital responsibility. And it's not just those. In early 2024, the 2-ton ERS-2 Earth observation satellite came down after its mission ended way back in 2011. A year earlier, in 2023, NASA's 300-kilogram RESI Solar Observatory re-entered over the Sahara Desert. This trend is speeding up. On average, a piece of tracked space junk, like a spent rocket body or a dead satellite, makes an uncontrolled re-entry about once or twice a week. Each one is a roll of the dice. The ticking time bomb in orbit, a satellite falling on your head, is the immediate, gut-level fear. But the much greater danger is what's still up there. As of mid-2026, space surveillance networks are tracking about 45,000 objects larger than 10 centimeters. Of those, only around 15,800 are active, working satellites. The rest, nearly 30,000 objects, is junk. This includes thousands of spent rocket bodies and tens of thousands of fragments from past orbital breakups. And that's just the stuff big enough to track. Models from agencies like ESA estimate there are over 1 million pieces of debris between 1 and 10 centimeters, and maybe 140 million fragments smaller than 1 centimeter. Why does a tiny paint fleck matter? In orbit, speed is everything. At 28,000 kilometers per hour, even a 1 centimeter piece of debris hits with the kinetic energy of a heavy object dropped from a skyscraper. A slightly larger piece can strike with the force of an explosion, more than enough to destroy a multi-million-dollar satellite. This leads to the ultimate doomsday scenario for our orbital neighborhood, the Kessler Syndrome. First proposed by NASA scientist Donald Kessler in 1978, it describes a potential chain reaction. A collision in orbit creates a cloud of debris. Each piece of that debris becomes a tiny projectile that can cause another collision, creating even more debris. If the density of objects in a particular orbit reaches a critical point, this process could become a self-sustaining, runaway cascade of destruction. If that happened, low Earth orbit could become a hazardous minefield for generations, potentially crippling the global infrastructure we all depend on for GPS, communication, and weather forecasting. Some experts, including Kessler himself, have argued that some orbital regions may already be at a point where this cascade effect is inevitable without intervention. The solutions: a cosmic cleanup. So, how do we fix this mess? The first step is to stop making it worse. International guidelines now recommend that new satellites be designed to deorbit themselves within 25 years of their mission ending. It's important to know, this is a non-binding guideline, not a strictly enforced law. This usually means saving a little fuel for a final disposal burn to send the satellite into a controlled re-entry over a remote patch of ocean, like the South Pacific uninhabited area, nicknamed Point Nemo. But what about the junk that's already up there? This is where active debris removal, or ADR, comes in. Several companies and space agencies are developing some incredible space janitor technologies. The European Space Agency is funding the Clear Space 1 mission, which aims to use a 4-armed robot to capture and deorbit a defunct satellite. After some delays, that mission is now planned for 2028. Other wild concepts being tested include giant nets, harpoons, and even powerful magnets. Astroscale's ELSA-M servicer is being designed with the goal of capturing multiple satellites in one mission, though its launch has been pushed to 2028 or later. The legal side of things is also crucial. The 1967 Outer Space Treaty and the 1972 Liability Convention state that nations are responsible for the objects they launch and are liable for any damage they cause. But proving who's at fault for a collision with a tiny, untraceable fragment is nearly impossible, which makes enforcement incredibly difficult. The threat of a satellite falling on your head, while a terrifying thought, is statistically minuscule. For an individual, the annual odds of being struck by lightning are in the ballpark of 1 in 500,000. While the odds of being hit by space debris are many, many times lower than that. But the re-entry of every satellite is a stark reminder of the real problem: the orbital highways above our heads are becoming dangerously cluttered. The risk isn't so much to you as an individual on the ground, but to all of us as a global society that relies on the infrastructure in space. The Kessler Syndrome isn't just a sci-fi trope, it's a real and growing possibility that we have to work to prevent. By designing better satellites, developing cleanup technologies, and holding nations accountable, we can ensure that low Earth orbit remains a usable resource for generations to come. We just have to decide to clean up our cosmic backyard. So, what do you think is the most promising way to clean up space? And who should have to pay for it? The nations and companies that created the most debris? Let us know your thoughts in the comments below. If you find yourself fascinated by the future of space, make sure to subscribe and hit that notification bell. We dive into the biggest questions in science and technology every week. Thanks for watching, and as always, keep looking up.